combination of series, a few special series, and try and see. You must remember these three series that I'm going to tell you. One, of course, is what is called the sum of the first n natural numbers. Sn, which is 1 plus 2 plus 3 plus n. Right? Now this of course is an arithmetic progression with first term 1, last term n, number of terms n. Right? So the sum of the sequences, sum of this arithmetic progression is going to be n by 2 into first term plus last term. So last term plus first term. So n into n plus 1 by 2 is the sum of the first n natural numbers, right? This is one result, which is an ordinary arithmetic progression, right? Or some of you might want to look at it like this as well. If you look upon this as Sn, n minus 1, etc. Write this sequence in a reverse order, which is called the method of reversals. Last term first, so that's going to be n plus n minus 1 plus n minus 2 plus 2 plus 1. Yes or no? I've just written last term first and proceeded in that direction, right? Now if I add them vertically, this is 2 times Sn. That's going to be, this plus this is n plus 1, right? This plus this is n plus 1. This plus this is n plus 1. Going this way. This plus this is n plus 1. This plus this is n plus 1. Right? How many such n plus 1s? N, right? This is the first group, this is the second group, third group, nth group. N such n plus 1s. So this is going to be n into n plus 1, right? So Sn 1 by 2, n into n plus 1 by 2. That's the sum of the first n natural numbers. Clear? Clear? Now let's look at the sum of the squares of the first n natural numbers. Sum of the squares of the first n natural numbers. By the way, how many of you understand what an equation is and what an identity is? What's an equation? What's an equation?
Equation will be in terms of variables, and it may or may not satisfy all the values of it, but an identity has to satisfy all the values that we are providing to the variables.
Okay, you're right. You could have stated that a little better. Both, right now, both an equation and an identity, these are mathematical statements. These are statements, right? When I talk of an equation, it's a statement, let's say, something like x square minus 1 equal to 0. This is a statement. Now, this statement is true either for no values of x or only for some values of x. That's what this statement is true. It's not true for all values of x. It has its limitations. If I say, so in this case, for example, it's true only for x equal to plus minus 1, 2 values of x, right? Then if I have a statement like x square plus 1 is 0, and if x is a real number, and if x is a real number and x square plus 1 is 0, then this statement is true for no values of x, right? Of x, as long as x is real, it's not true for any real values of x. If I have sin x equal to half, for example, how many values of x is it true for? No, infinite values. If you have seen my class on trigonometry, this is true for infinite values of x. Right? X equal to 30 degrees, 30 degrees plus 360 degrees, 30 degrees plus 720 degrees, and so on and so forth. You can go on forever, right? So this is true for infinite values of x. But not true for all values of x. I mean, it's not like if you put x equal to 0, this will be true. This is true, but has a discretion, has a choice. It will be true. This is a statement true not for all values of x. This is a statement true for finite values of x. This is a statement true for no value of x. This is true for infinite values of x, but not for all values of x. Right? In contrast, if I have a statement like x square plus 1 equal to x square plus 1, this is true for all values of x. Indiscriminately true for all values of x. See, this also has infinite number of values of x for which this is true. This also has infinite values of x for which this is true, but this is true not for every value of x. Infinite set of x for which this is true, but not for all values of x. This is true for infinite and all values of x. Yes or no? Right? So this a statement which is true for infinite set of values of x and for all values of x, indiscriminately true for all values of x, is an identity. A statement, a mathematical statement which is indiscriminately true for all x is a identity. This is an identity. Whereas these are statements not true for every value of x. Either they could be true for no value of x, they may be true for finite, they may be true for infinite, but not for all values of x. These statements fall under the category of what's referred to as an equation. Whose was that? Oh, really? It's your birthday? Many happy returns of the day. Your ringtone is very good. Maintain the ringtone, but don't let it spring into action in the next class or after that. But many happy returns of the day. I'm not going to spoil your day. No, that's okay. Your birthday saved you today. So, these fall under the category of what's referred to as an equation, and this is an identity, true for all values of x. If I write like x square minus 1 is x plus 1 into x minus 1, what is it? An identity, right? If I write like x cubed plus 1 is x plus 1 into x squared minus x plus 1, what is it? An identity, right? If I say sine squared x plus cos squared x equal to 1, then what is it? An identity. Yes or no? Right? So an identity is a statement which is true for all values of the variable. An equation is a statement which is true. No, it may not be true for limited values. It's not true for every value of x. It may be true for infinite, which is unlimited values of x. For example, this is true for unlimited values of x, but not true for all x. Right? That's the subtle difference. Clear? Now, suppose I have r cubed minus r minus 1 whole cubed. Let me simplify matters here. R cubed minus r minus 1 whole cube. Let me simplify this expression. Clear? This is like a r cubed minus. A minus B whole cubed is what? A cube minus B cube minus 3A squared B plus 3AB squared, right? All of you know that? So A cubed minus 3A squared B or AB squared? A squared B plus 3AB squared minus B cubed. Yes or no? Clear? Right? This is like a 3R squared minus 3R plus 1. Yes or no? Is this true or not? Right? So R cubed minus R minus 1 whole cubed is equal to this. Is it an equation or an identity? It's an identity. It's an identity. It is true for R equal to London, R equal to Hong Kong, R equal to Patna, R equal to anything. Right? This is an identity. So if there is an identity, you enjoy the luxury of plugging in any value of R that you want. Right? So let's start by doing the following. Let me plug in R equal to 1. Right? Let me plug in R equal to 1 on both sides. So I end up getting 1 cubed minus 0 cubed equals 3 into 1 squared minus 3 into 1 plus 1. Right? Yes or no? If I plug in R equal to 2, 2 cubed minus 1 cubed is 3 into 2 squared minus 3 into 2 plus 1. Right? Similarly, R equal to 3. 3 cubed minus 2 cubed is 3 into 3 squared minus 3 into 3 plus 1. Right? Going this way, if you plug in R equal to n, you get n cubed minus n minus 1 whole cube is 3 into n squared minus 3 into n plus 1. Yes or no? Sounds good? Now let me add all of this. Let me add all of this. Let me add all of this. If I add all of this, you realize that there is a convenient cancellation of terms. 1 cube would get cancelled with 1 cubed here. 2 cube would get cancelled with 2 cubed here. 3 cube with 3 cubed. N minus 1 cube would get cancelled with a n cube there. What are you left with? N cubed and 0 cubed on the left hand side. These are the two unattended terms on the left hand side. N cubed and 0 cubed. Sounds good? Right? So that gives me n cubed equals 3 into, if I add these and then these and then these, that's how I'm going to add, right? 3 into 1 square plus 2 squared plus 3 squared plus n squared, right? Minus 3 into 1 plus 2 plus 3 plus n plus 1 plus 1 plus 1 plus 1. How many times? N times, and therefore n. Yes or no? Right? Now, suppose, what is this? Sum of the squares of the first 10 natural numbers. 1 square plus 2 squared plus 3 squared plus 4 squared plus n squared is sum of the squares of the first 10 natural numbers. Clear? Right? So, I designate that as Sn. Sn is sum of the squares of the first 10 natural numbers. Sum of the squares of the first 10 natural numbers. That's what this is. Right? 1 plus 2 plus 3 plus n. Sum of the first 10 natural numbers, which is n into n plus 1 by 2, like we just figured out a little while ago. Right? So, 1 plus 2 plus 3 up to n, that's going to be n into n plus 1 by 2. Right? Yes or no? Okay. So then n cubed equals 3 times 1 squared plus 2 squared plus n squared, which is sum of the first n natural numbers, minus 3 into, this is 1 plus 2 plus 3 plus n, which is n into n plus 1 by 2, plus n. Right? Yes or no? Right? Now if you simplify matters here, 3 times Sn. 3 times Sn is n cubed minus n plus 3n into n plus 1 by 2. Right? Which is like n into n squared minus 1. That means n into n plus 1 into n minus 1. Right? Plus 3n by 2 into n plus 1. Yes or no? Do you realize that? I took n common from this, so n squared minus 1, which could be rewritten as n plus 1 into n minus 1. Then plus 3n into n plus 1 by 2. Now from the whole thing, I could take n into n plus 1 by 2 common. Right? That will leave me with 2 into n minus 1 plus 3 by 3. Right? Which really reduces to 3 times Sn, 3 times the sum of the squares of the first 10 natural numbers equals n into n plus 1 into 2n plus 1 by 3. That's 3 times Sn. See? This would be 2n plus 1 minus 2 plus 3 is 2n. Sorry, by 2. Right? Isn't it? So that gives me Sn equals n into n plus 1 into 2n plus 1 by 6, which is the sum of the squares of the first n natural numbers. Sum of the squares of the first n natural numbers. Sounds all right? So this is again an important result to remember. Sum of the first n natural numbers, n into n plus 1 by 2. Sum of the squares, n into n plus 1 into 2n plus 1 by 6, and so on and so forth. Can I wipe this off? Sounds all right? Similarly, you would also want to know some of the cubes of the first 10 natural numbers. Some of the cubes of the first 10 natural numbers. Now, if you look at this identity, r to power 4 minus r minus 1 whole to power 4. Hey, by the way, do you know this? A plus b plus c whole square is a square plus b squared. Okay. That was in unison. Very good, very melodious. Thank you. Right, maintain these energy levels in the class. Maintain this synchronicity with the symphony that you spread in the class. That's wonderful. Okay, right? Now, this r minus 1 whole to power 4 is actually what? R squared minus 2r plus 1 whole squared. R minus 1 whole squared? Square of that, right? R squared minus 2r plus 1 whole squared, isn't it? Do you all understand this? Then this is like a plus b plus c whole square. So I can deploy that result, right? So if I deploy that result, that's going to be a squared plus b squared plus c squared plus twice this into this, which is minus 2r cubed, plus this into this, which is this into this, which is r squared, and this into this, which is minus 2r. Yes or no? Do you all understand this? I've just deployed this formula. Which then is like r to power 4 plus 4r. I'll write this minus 4r cubed plus 6r squared minus 4r plus 1. Tell me, do you understand this? See, r to power 4 minus 4r cubed plus 4r squared plus 2r squared, that is 6r squared, minus 4r plus 1, just consolidating terms systematically. Right? Clear? Is there any confusion on this? No. Of course, after I teach you binomial expansion, we will not, complicate matters like this. We'll give you simpler ways of expanding anything. But for the time being, just a makeshift arrangement, this should be all right, right? So this then is like a r to power 4 minus r minus 1 whole to power 4, which is this. Is that okay? Is that all right or not all right? So then, and what is this? Equation or identity? This is an identity, yet another identity. Clear? This then is like a 4r cubed minus 6r squared plus 4r minus 1. Right? And now I plug in r equal to 1, 2, 3, etc. successively. I plug in r equal to 1, 2, 3, etc. successively. So if I plug in r equal to 1, I get 1 cubed minus 1 to power 4 minus 0 to power 4 on the left hand side. Plugging in r equal to 1 on both sides, that's equal to 4 into 1 cubed minus 6 into 1 squared plus 4 into 1 minus 1. Right? Plug in r equal to 2. 2 to power 4 minus 1 to power 4. 6 into 2 squared plus 4 into 2 minus 1. Right? Going this way, plug in r equal to n. So n to power 4 minus n minus 1 to power 4 equals 4 into n cube minus 6 into n squared plus 4 into n minus 1. Do you see sense in this? Yes or no? You know what the intention of doing all this is? You know what the intention of doing all this? When I looked at the earlier identity r cube minus r minus 1 whole cube, the intention was to find the sum of these squares. When I do this, then my intention is to find the sum of the cubes of the first 10 natural numbers. That's the intention here, plain and simple. You know, that's the objective of carrying out this exercise. I now want to find the sum of the cubes of the first 10 natural numbers, right? So now I perform a customary vertical addition here, right? What's going to happen is this will get cancelled with this. This would have got cancelled with this. This would have got cancelled with the term here, leaving you with how many terms unattended? N to power 4 is the only unattended term on the left hand side, yes or no? Yes. Right. So then if that's the only unattended term on the left hand side, then n to power 4 on the left hand side. And now let's deal with the right hand side. Right? This 4 into 1 cube plus 2 cube plus 3 cube plus n cube, which is 4 times the sum of the cube of the first 10 natural numbers. I'm calling it Sn, sum of the cubes of the first 10 natural numbers. 4 into 1 cube plus 2 cube plus 3 cube plus n cube, which is sum of the cubes of the first 10 natural numbers, which I'm designating as Sn. Okay. Minus 6 into 1 squared plus 2 squared plus 3 squared plus, yes, which is sum of the squares of the first 10 natural numbers, yes or no? Yes. Right? So which is, and sum of the squares of the first 10 natural numbers, like we figured out, is n into n plus 1 into 2n plus 1 by 6. Yeah. And then next one, 4 into plus 4 into 1 plus 2 plus 3 plus n, which is n into n plus 1 by 2. Right? And then minus 1, minus 1, minus 1, minus 1, n times. So that makes it minus n. Let me tell you the final result that associates with it. You would want to do the simplification yourself. Sn, let me tell you, will then turn out to be n into n plus 1 by 2 whole squared. Right? Sounds all right? So now you know sum of the first 10 natural numbers, sum of the squares of the first 10 natural numbers, sum of the cubes of the first 10 natural numbers. Not that you want to keep doing this a lifetime. Sum of the fourth powers of the first, sum of the fifth powers.
So sum of the natural numbers to the power n.
To the power k?
To the power n.
To the power n? Where?
Yes,
What? What? Sum of the?
Natural numbers first in natural numbers to the power n.
To the power n. That means 1 to power n plus 2 to power n plus 3 to power n plus n to power n.
I had seen it.
You can't get that this way. That means 1 to power k plus 2 to power k plus 3 to power k plus n to power k. There is no result for that. You have to binomially expand that and you will get that not as a condensed form. Trust me. This method is called Onky Jonky Gori Dori method. Oh, if only I had a name known for this method, I would have shared it with you. Now that there isn't a name known to me, let me call it Onky Donkey Jonky Jori Dori method. Right? What's in a name? You call it Raj method, yaar. Right? Does not matter. Call it Raj method. What's there in a name, yaar? The person who made it, you can call him Raj, right? So what? That's the way it is. There can be multiple Raj, right? First of all, I do not know the name of the person who did this. All right. Second, I have not known of a name associated with this method, right? So let's not bother about the history and names. Let's bother about the techniques. Okay, Raj? But we'll call it the Raj method from now on, right? Yeah, way to go. I in fact will take time out and introduce you to someone extremely enlightened. Just call Shayan. Shayan Bushe ache na? Beto. I've so happened that one of my no, recorded. Let it get recorded. Call him. This is an ex-student of mine, but let him come down. Shayan to Ashby. Extremely modest fellow, but I have to introduce him to you. Please come, Shayan. He feels very shy. He's a downright academician. He was my student from class 10 onwards. When he was in class 10, he was attending class 11. When he was in 11, he was attending 12. And when he was in 12, he was attending 12. Okay. But not that he needed to attend. Extremely bright person. He has just passed out of ISI and is the topper from ISI. So can we give him a big hand, please? And Shayan, if I have to tell you the least about him, and he's heading for a PhD. He's going to Chicago for his PhD. He's got funded for a PhD program in the US in discrete mathematics. Now, I'll tell you one very, his elder brother, Shabbir Sachi, was also my student. So then, when he was still in class 10, his elder brother brought him to me. He said, "Sir, okay, class attend korte din. Bhalo ache, khub bhalo ache." So I said, "All right, let me check him out." And I started pouring problems on small kid, class 10. Now he has beard, but that time he didn't. So he looked like a real kid. And when I started shooting problems at him, first I shot inequalities. I didn't realize that he's the king of inequalities. He's world number 1 in inequalities. Okay. He said this. I said, this kid, how does he know all this? You know, this one will be this one will be that. Everything that I shoot at him, you know, he comes up with an answer. And then I gave him another. I still remember I asked you, solve x power y is y power x. He said infinite descent. You remember that? I said, God, he has the maturity and the knowledge all in one place. I was zapped. I said, all right, he was still in class 10 and he was attending class 11. And no, that's his phone. That's all right. He's now eligible to, you know, keep it on while I'm talking. And then he would sit here and, you know, with his seniors, class 11 students. And after a while, so every time there was, so the first sessions, few sessions were trigonometry sessions, and he would just quietly do problems, and then some seniors of his started complaining against him. They came up to me, said, "What's the matter?" People stopped sitting in the first bench. He was the only. Said, "What's the matter?" They said, "He gives us a complex. He gives a complex to the rest of the people in the class. So they don't want to sit next to me. They feel very threatened, very worried. class 10 students sitting with class 11 students, some of them very good actually. One of them was, Manav was your classmate? Manav Kedia, who just finished his BTech in computer science from IIT Kharagpur, and he's heading for University of Urbana-Champaign for a master's. So he said, sir, किसके पास बैठा दिए? ये तो danger man है. I mean, he's like a live wire. Everything he has a better, smarter, superior solution. God knows what he's up to. He said, I feel very scared. So people stopped sitting next to him. But then, of course, a core mathematician, a core academician, he journeyed for 3 years with me. And I would say, it's not that every time he learned from me. There were times I learned from him too. Initially he was a threat to everyone in the class, but then let me tell you, the inside story is he became a matter of inspiration to everyone in the class. He was inspirational because he was 1 year younger. He was in a junior class, and things happened. So, and then of course he went to ISI. He just walked into ISI with aplomb, with confidence, and with ease, almost effortlessly. And then he's now finished his undergrad at ISI. The final year results are pending, but until then he's ranked #1 there. So to be the topper at ISI again is no modest achievement, right? Is something one would really want to be envy. I do not know if Cheyenne would want to say anything, but if he does, one thing, reason I brought him to the stage right now, coincidentally he was here, is because his radiations might help, right? He would radiate a lot of intellectual wisdom, strongly packed mathematics, and in his electrical influence, you will feel extremely rewarded. You won't realize. You would go back home and suddenly feel, hey, you are now mathematically inclined. This is how you'll begin to feel. He's not liking it because he's modest, not at all outlandish. I do not know if he wants to say something. I will only ask him if he has anything to tell them. He's a reserved individual, but with his background, you would realize he's packed with a lot of grey matter and beyond. But Cheyenne, anything for these kids that you want to say?
Do whatever you like.
Do whatever you like, which is what he did, and that's very plain and simple. Do whatever you like, but do it well. पाप हो या पुण्य हो, कुछ भी मत करो अधूरे मन से. That's the rule of life. That's the fact. Do not take chances with mediocrity. Do not take chances with mediocrity. If you have to become a goon, become the biggest goon. Don't become an ordinary पाड़ा का दादा and say मारिश तो मारिश गाय हाथ दी बिना. Don't become one like that. Otherwise they'll say, hey, আমাকে ধর তো. As if people didn't hold him back, he would create chaos, commotion, and disruption everywhere on the planet. Yes. So, if you have to become a goon, then I'm not saying don't communicate it to your parents, then become Dawood Ibrahim if you want to. Everyone will be scared of. What's the point in pursuing mediocrity and living with a useless thought of mediocrity? That is pointless in life. Okay? Work with tremendous gumption, tremendous courage, with a zeal to excel, with a zeal to be empowered in whatever you want to do. That has to be the foundation of life, foundation of living, and whatever you want to be able to do in life. I'm not sure if you're aware, this fellow is not there in the class today, but Chandak, Raghav Chandak. Raghav, how many of you know him? He featured in the newspaper this time. Do you know what he went through and how he conquered his disease and went on to do so good in ICSE? that's again very inspirational, very inspirational. He has a school fest which he's attending today, but uh, you know, this is true metal. This is how you have to be. You cannot you cannot be flimsy. You cannot be half-hearted. You cannot settle for less. You have to live life king size. You cannot compromise in what you do. All right, and like I said, the difference between ordinary and extraordinary is just that extra, just that little extra. You have that extra in you. It's for you to identify that extra and kindle it. It's just requires kindling. One step of kindling, and it's going to give you fire that's not going to burn you. It's going to promote you to the next echelon of living, the next echelon of intellectual thinking and action. This is how it has to be. Don't live with mediocrity. Don't even strive to be an average person, an ordinary person. No extraordinary person is just born extraordinary. He makes himself extraordinary, and that is the thought that should, be with you all the time. We've had his philosophy. Hey, one thing he said, our friend Raj asked me a name for this method. Of course, in general it's called telescope, when you have cancellation of terms, but this is that writing that identity is not telescope. Writing an identity like this, he asked me a name for this identity. Do you know a name for this identity? I said, I don't know of a name for this identity, so I named it after him. We'll call it the Raj identity. With your consent, so he has the consent. So now the mathematical community, under his tutelage, under his aegis, has accepted that this identity henceforth would be referred to as Raj identity.
Difference between consecutive cubes.
Right? Adding the whole thing is called a telescope when there is a cancellation of that kind, but otherwise this identity will be referred to as Raj identity. Right? Do you all accept this without resistance? Right. Okay.
Some of the Raj identity over
Wow. Some of the Raj identities over natural numbers would give me the required result. Right. All right. That's the way to go. The other day when I was sitting with Shrish Maharaj, he mentioned to me that something. Have you read the Gödel's incompleteness theorem? No. Okay. We'll then talk about it later. I was very thrilled about that Gödel's incompleteness theorem, and essentially I realized that most of the things that we end up proving in mathematics at this level, they are first order. And we given A, we actually end up proving A only in a different form in first order mathematics, right? In second order, there still is something else. But I thought he'll throw light on that. But at some other point of time, once he comes back with his PhD, we'll ask him to talk mathematics, philosophy, and religion. Thank you. I will not bother you very long. ভেতরে গিয়ে বস, আর কিছু অন্য কিছু যদি বলতে চাস তো বলে দিস। আর কিছু বলার আছে? Huh? Thank you so much. Remember, you'll be a lot better in mathematics at the end of this because of his presence. You have been in his electric field. Thank you. Thanks, Shayan. Right.